What I would like to do now is take you through a short lab exercise showing you how to calculate orbits. We've spent the last roughly hour or so talking about Kepler and Sir Isaac Newton and the arithmetic, and we touched a little bit on the arithmetic associated with calculating orbits. It's really not as hard as you might think. Now, we'll start with this first example on page 40A. Example number 1. Using Kepler's third law, we're going to determine the mean or average distance in astronomical units of Jupiter from the Sun based on its orbital period in Earth years. Now, what you need to understand is when you are using Kepler's third law, p squared equals a cubed, in this application, p is measured in Earth years, a is measured in astronomical units. So those are the units that we will use using Kepler's third law. In this case, the period of Jupiter's orbit is 11.862 years. You can find that in the appendix of your textbook. So all we have to do now is just run the formula. And we invoke that time-honored tradition in physics known as plugging and chugging. We're just going to plug in the numbers and let them rip. So P is 11.862, so now that's going to be 11.862 squared equals a cubed. So 11.862 squared. I'm showing 140.707. Okay, that equals a cubed, but I want a. So how do I uncube something? Cube root. So a is going to equal the cube root of 140.707. There it is. And I get 5.201 AUs. And you can check that in your book. Yeah, Jupiter averages 5 astronomical units from the Sun. The Jupiter is roughly 5 times the distance to the Sun that we are. All right, so pretty straightforward. Let's try another example. Example number 2. Using Kepler's third law, let's determine the period of Mars' orbit based on its mean or average distance from the Sun. And the data we will use is A equals 1.5237 AUs. So again, we set up our equation. Okay, so now we know that p squared is going to equal 1.5237 cubed and I get 3.538. All right, that's p squared. I don't want p squared, I just want p. So how do you unsquare something? You square root it. So p is going to equal the square root of 3.538. And I get 1.881 years. And yes, that is the period of one Martian orbit. That's one Martian year, 1.881 Earth years. All right. Now we'll turn to page 40B, and now we're going to deal with Newton's version of Kepler's third law. Now, when you are dealing with Newton's formulas, the thing you must keep in mind is we now have to use standard units. So when we're talking about distance, if it's one of Newton's laws, the distance has to be in standard units, which are going to be either feet or meters. We'll stay metric here. In terms of time, we cannot use years, we can't use hours, we've got to use seconds. So always keep that in mind when you're dealing with any of Newton's formulas. You got to use standard units, otherwise it's just going to be a mess. So we have to be careful about using standard units. So our first example here is using Newton's version of Kepler's third law. We're going to determine the period in days of Jupiter's moon Ganymede. So Ganymede's orbital radius, that would be A, is 1,070,000 kilometers. All right, now we cannot use kilometers. We have to convert that to meters, and we better use scientific notation. So, very carefully, kilo is 10 to the third, all right? And then I'm going to go 1, 2, 3, 4, 5, 6. All right, just be careful. 1, 2, 3, 4, 5, 6 places to the left. All right, so my decimal's going to go up. So that's going to make it 1.07 times 10 to the 9th meters. Okay. So now I'm going to use Newton's version of Kepler's third law, where the square of the period is 4 pi squared a cubed over gm. So we'll plug in our values. A is going to be 1.07 times 10 to the 9th cubed over G, 6.672 times 10 to the negative 11 times my mass, which is, oh, I have to convert my mass. No, I don't. My mass is already where it needs to be. My mass is, I'll put this down here for my list, 1.899 times 10 to the 27th kilograms. Okay, so 1.899 times 10 to the 27th. All right, so now all my numbers are in there. And now you see the value of scientific notation. So now we're just going to carefully walk this through one step at a time. That's the key. So 3.14 squared, 9.8596 times 4. I got 39.438. Now I'm going to cube this, 1.07 to the third power, 1.225, 1.225, 10 to the 9th cubed is 10 to the 27th. And I'll go ahead and multiply these. 6.672 times 1.899. I got 12.670 times 27 minus 11, that would be 10 to the 16th. Now I'll multiply that. 39.438 times 1.225 at 48.312 times 10 to the 27th over 12.670 times 10 to the 16th. Now I'll divide. And I got 3.813 times 27 minus 16, that would be 11. Okay, that's p squared, remember, all right? So, p squared equals 3.813 times 10 to the 11th power. But I don't want p squared, I want just plain p. How do you unsquare something? You square root it. But wait a minute, I have an odd numbered exponent here, so I'm going to cheat. P is going to equal square root of 38. .13. All right, I moved my decimal to the right. That means my exponent goes down, 10 to the 10th. All right, so now square root of 38.13 equals 6.175 times 10 to the, divide the exponents by 2, 10 to the 5th seconds. All right, so that's Ganymede's period in seconds. But the answer we want in days. So we're going to convert seconds into days. All right, fairly simple proposition. So I've got 6.175 times 10 to the 5th seconds. I'll make it look like a fraction. And now I'll set it up so that I can cross cancel my terms. I'll cross cancel seconds and replace them with hours. And then I'll cross cancel hours and replace them with days. 3.6 times 10 to the 3rd seconds makes 1 hour. 2.4 times 10 to the 1st days makes 1 day. Now I can cross cancel. And what I'm left with is 6.175 times 10 to the 5th days over 3.6 times 2.4 times 10 to the 3rd times 10 to the 1st, 10 to the 4th. 3.6 times 2.4, 8.64. So now I have 6.175 times 10 to the 5th days over 8.64 times 10 to the 4th. So now I'll just divide these. 6.175 divided by 8.64, and I get 0.715 times 10 to the 1st days, or 7.15 days. What do you know? And you can check that again. You can check that with the appendix in the textbook. So there, that's how we can calculate the period of the orbit of Ganymede. Pretty straightforward, but I hope that the biggest takeaway here is how valuable it is to be able to manipulate these ridiculously large numbers in scientific notation. We wouldn't be able to do this stuff otherwise. So we have one more to show you after this one, and so we'll see you on the other side.